Okay, can you hear me?
Yes, we can hear you.
Okay. Okay, good evening, everybody. So last lecture, we started to talk about the last topic in the batch of lectures in kinematics. And we were introducing some concept of linear algebra that are spaces that are useful to analyze both redundancy and singularity. And we introduce in the specific the concept of null space that is the set of joint velocities that do not produce any motion at the end effector. So think about this kind of motion. So the end effector is not moving, and this joint move in a certain configuration of joints velocities that produce no motion at the end effector. The null space always exists whenever the robot is redundant. And also we talk about the range space that is the set of end effector velocities that can be realized instantaneously, we remember, because we might change the configurations and the definition of these spaces changes with the configuration. So it's only local with the actual configuration. And is a set of effector velocities that can be realized varying with some joint velocities. So in a certain configuration, we have a set of joint velocities. We produce an end effector velocity, and the whole possible end effector velocity that are realizable with any combination of joint velocities, then is the range space. And of course, if the we said that if the rank of a Jacobian is maximum, for example, in the case M times N matrix, it's M, then we can cover all the space and the vector space, and we can move in any direction. While if there is a rank deficiency, a reduction of the rank of the matrix J, it means that there are some directions where the end effector cannot move. And these directions we will see that are the singular directions. But first, let's talk about the null space. Sorry, the redundancy and its relationship with the null space. So a null space always in this case, if we are talking of a redundant robot, it means that we have more columns than rows. So the null space will be existing in the domain, and exactly can exist only whenever the rank of the J matrix it's smaller than the number of joints of columns. So in the case of a redundant robot with n bigger than m, where m is the dimension of the task space that is full rank, the dimension of the null space will be n minus m. So if we look at the shape of a Jacobian matrix, we see that it is rectangular, and we call this fat matrix. And in this case, we said that we will show some tricks to compute the inverse of the differential kinematics, because since we have more columns than rows, if we want to compute the joint velocities relative to some end effector velocity, we will have infinite solutions. And to solve this, we resort to the concept of pseudo-inverse. And you can find the mapping. Between V and Q dot as J pseudo inverse V, and we call this pseudo inverse of J, plus we can add some other component that we call the null space component. And this component will have no effect on the end effector velocity. So it won't change, in essence, the achievable velocity, but can be used, for example, for another secondary task. And to compute this component, the null space component, we use the so-called null space projector. That is this matrix computed as I identity minus J pseudo inverse J, and it's called the null space projector matrix. That does what? Given a task, for example, in the joint space, filters out whatever velocity will produce some end effector motion, and will allow only the motions that are in the null space. So, for example, these motions. We call this null space method in the kinematics. Then, what we can do with this other task? We can define, for example, secondary task. For example, a postural task that will not influence the end effector. So think about, we want to try to achieve some favored configuration that maximizes dexterity. So we locate the end effector, and then we, of course, this configuration, for example, to push in this direction would be less convenient than this one. So you might use the postural task to rearrange the redundant joints, the redundant part of the configuration, of the joint configuration, to achieve some other task, a secondary task, without affecting the first one. Yes? Is Q dot 0 belongs to the set of Q dot. Of course, yes, it belongs to the domain, but we don't care. We don't want to design Q dot 0 in a way that doesn't influence V. We want that the null space projector does for us, and we just care to define a secondary task, which is easier. And we see here where Q dot 0 is projected to. So Q dot 0, let's say, think about this is the domain. This is not really the best way to draw it, but I couldn't find a better one. And in essence, what it represents is that the domain of Q dot is mapped into the range space of J, where that is part of a codomain. And in this case, let's say it is coincident with the codomain. And we have the null space part that is mapped into zero velocity. If we have a secondary task, Q0 dot, that will have, let's say, two components, one in the row space and one in the null space. If we multiply for the null space projector, this will be in this set, and so will have no influence. While if it is in this set, this will, through J, will go into the range space, and so affect V. The opposite is the J transpose. In this case, we want to map V into joint. So we want to achieve V with some joint velocities. And this set of joint configuration that we realize this will be here. Plus, we add the null space component that will not affect the principal task, that is achieving some end effector velocity. And so to show you how the null space works, we should say that if you have the null space projector here, that projects this Q, if we multiply by J, we'll end up into 0. So from here to here. And we call this row space projector because we said that null space and row space are orthogonal. So they both sum up to the identity if you sum them up. And so row space projector plus null space projector is equal to the identity. And the row space projector is something that does like this. If you multiply some Q dot whatever that might have a null space component times the row space projector, you see that you go from Q dot, you go through J into the range space. And then through J pseudo inverse, you go to the row space. So you're sure that even if you have a null space component, you will have filtered out and will be in the row space project, in the row space. So as I said, we can implement some other tasks for the dexterity, for example, postural task. For example, we want to achieve a certain configuration, default configuration, and try to stay close as possible to that configuration. Maybe the one that is in the middle of the range, of the joint range, for example. But the question now is how to compute these pseudo inverses that we defined, and we need to understand how to compute. So first, the pseudo inverses are necessary if you want to invert a rectangular matrix, because I mean, the inverse of a matrix exists only in the square case. And because these matrices are rectangular, and they can be of two types. They can be fat or skinny, according to the fact that they have a bigger number of columns, of rows. Sorry, they are fat is a bigger number of columns, or skinny, a bigger number of rows. And at first, we assume that the matrix A is full rank. We want to compute the pseudo inverse of this matrix, while in the skinny case, the matrix is like this. And in this case, the fat case, the pseudo inverse is as the row and the columns that are flipped around. And how does it look like? So think about how, as a mnemonic trick, you need to think what does it take to what will be the matrix that is invertible here? So we need to make an invertible matrix, and we can do that if, for example, we know that the maximum rank it's M, we say A is full rank. So if we multiply A times A transpose, we get an full rank M times M square matrix that we can invert times to achieve this shape. This is an M times N. We need to multiply by N times N. Okay? And this is achieved, for example, by transposing A. So this is the pseudo-inverse computation in the fact case. One in the skinny case. Can you tell me? We want to achieve this shape. What should we do? We need to use the same trick. So this time we have smaller n than m. So we want to do something like this to achieve n times n matrix, which is could be invertible and square. So we do A transpose, which is as this shape, times A, which has this shape, and we can invert it. Then to achieve this shape here, from this shape here, we need to post multiply by A transpose. Okay, because we get something like this. Okay, and this is the computation of pseudo-inverse in the case of a skinny matrix. Any question? Now, assume that the rank is not full. So the trick that we used before is no longer valid, right? Because we get a singular A transpose or A transpose A matrix. However, the math theory says that, algebra theory says that still the pseudo-inverse exists and can be computed numerically, for example, with the singular value decomposition of matrix A. If you're interested in to know how the singular value decomposition works, I have a hidden slide that I can show you to the ones that are interested. And this is computed usually with the MATLAB function pinv. So the previous formulas are valid only in the case of full rank. Okay. Now let me give you some more notes on pseudo-inverses. So you need to think a fat matrix as something that maps from a bigger set to a smaller set. There are more unknowns than equations. Exist infinite solutions to the, for example, to the problem, to the inverse problem of getting. So if you think about ax equal to b, we have x here, b here. With the problem, inverse problem, we have infinite solutions. And the solution that we get from this, it's the one that minimize the norm as the minimum norm. So of all the possible infinite solutions that for which we can achieve the known term b, we get, doing the pseudo inverse, the one that minimize the norm of the of x. So we have infinite x and we get exactly the minimum norm one. In the case of skinny matrix, instead, we are mapping from a smaller set to a bigger one. So you have more an equation than unknowns, and a solution is not, exact solution doesn't exist. And if we do the pseudo inverse with the skinny case, we get out of it the, if you do the pseudo inverse, in this case, we get the best fit, which in a least square sense, that minimizes what? Minimizes the error between ax and b, because we said it's not possible to have an exact solution that satisfies ax equal to b, but the pseudo inverse spits out the one that tries to minimize this error, the norm of this error. And you can think about, for example, if you want to fit a set of points of B point, BE, they represent many points, and you want to fit with a line or with another function, the coefficient of this line are represented, for example, by the unknown x. You can find them out with the solving with a pseudo inverse approach. And this will, if you have many points, and of course, in the case of a line, you have two coefficients, then you will get the a least square solution that tries to minimize the residual error. This is called residual for each point. And we can also see the pseudo inverse solution as the solution of a optimization problem. First, let me recall again, because I think last time it was not so clear, what an optimization problem is. An optimization problem is a problem where we want to find the best solution from all the feasible solutions. And in general, in standard form, we want to minimize a function, a cost function called fx, that is function of what? Of a decision variable via vector of decision variables, subject to, in case we have a constraint optimization, some constraints. These are equalities, inequalities. But in our case, we will see that we use only the unconstrained case, so we don't consider any constraint. And if we want to maximize rather than minimize, best solution means to either minimize or maximize. If we want to maximize, we can rephrase the problem as a minimization problem, putting a minus against the constraint. And when we say argmin, it means that we want to, in this case, we find the minimum cost, so the minimum value of the cost. In this case, we find the minimum value of the value of the decision variable that minimizes the cost. So the optimal solution that minimizes f of x. Okay. Now, in case of a skinny matrix, we can cast the pseudo inverse as an optimization problem. And we said we want to minimize this error. So the pseudo inverse finds the optimal X that minimizes this residual error. And we can again express this norm explicitly. We compute product, this and this, plus this and this, which is plus the double product. And double product, because they are scalars, they can be summed up together because we have B transpose A minus A transpose B. And because they are scalar, they can be flipped and we can sum them up. So this was 1/2. This was 1/2, 1/2. We can sum them up. So the 1/2 will disappear and we get the B transpose A. Because they are scalars, so this one, the scalar of a transpose is the same as the scalar, so we can do the transpose and obtain the same as this, and so we can sum them up. Then we need to minimize, we say that the gradient of the cost f should be 0, so do the derivative of this with respect to what? With respect to the decision variable, and we find out that this is a quadratic term and the derivative is linear. It's like, that's why we put the 1/2, because it will become 2 A transpose AX, and this will nullify with the 1/2 here. Plus, this term doesn't depend on X, so we'll have 0 derivative, is constant. And this one, sorry, there was an X missing here, will be just minus A transpose B. So minus B transpose A. We set equal to 0. We rewrite this, AX, we put this on the other side. And then we get the solution that will be A transpose A minus 1, A transpose B. And this is exactly what we said is a pseudo inverse or skinny matrix that minimize the error. Okay. So we want to do the same for the fat case. We say that in the fat case we have the minimum norm solution, and we can discriminate two cases whenever A is full row rank. In this case, the solution is the one that minimizes the norm X, and this time subject to AX equal to B. So because it's full rank, the solution exists, is unique. The solution exists, but there are infinite solutions. And of this infinite solution, we take the one that has minimum norm. While in the case that matrix A is not full row rank, so its rank is smaller than the number of rows, then solution doesn't exist. So the pseudo inverse will provide the minimum norm solution of the ones belonging to the set S that represents the X for which this term is minimum. So we try to do the best that he can to solve the problem. It's not possible to minimize to zero, this as in this case.
We cannot hear you, Michele.
I hope, can everybody hear me now? I think it crashed, Zoom crashed.
Yeah,
How much did you miss?
I think was just this on the previous slide.
Okay. Yeah, in essence, I was saying that in case of a full row rank, we get from the pseudo inverse of a fat matrix the equivalent optimization problem that minimizes among the solutions the one that has minimum norm. Finds out among the solution the one that has minimum norm and solves the problem in an exact way, because we have full row rank, so infinite solution exists to the problem. In case the rank is not full, then it's not possible to solve the problem precisely. So we can only resort to minimize the error, and the pseudo inverse in this case will determine the solution that minimize the norm of the solutions that among the solutions that try to minimize the error AX minus B. Yeah, then we can have some geometric interpretation of what we wrote before. Remember, this is the row space projector, is a null space projector that filters out the row space component and projects it in the null space from Q0. And if we do a simple example to visualize this of case with a robot with two joints, Q1 and Q2 joint configuration space, and one task variable, we can see that of the solution that we get, that is the red one, we'll have the green one that represents the minimum norm solution, plus the null space component that is orthogonal to the range space component. And you see that this is the line of all the optimal, infinite optimal solutions that realize B. So among the infinite ones, I take the minimum norm ones, plus I can add the null space component that is orthogonal to the range space one and is not affecting B, and obtain the Q dot. Okay. So this is the line where this is true. Say Q dot equal to. Okay. Then we can define also a generalized pseudo-inverse. So far, what we called pseudo-inverse in reality is the more, it is a specific type of pseudo-inverse that is the Moore-Penrose pseudo-inverse. And people usually indicate it with the symbol A cross. Imagine a long symbol like this. If you use latex, it's called dagger. And there is a note. Penrose is the same one that won the Nobel Prize last year for the work on black holes and singularities with Stephen Hawking. So this is just a curiosity. And actually, infinite pseudo-inverses exist, but just by setting a weighting matrix into the pseudo-inverse computation. So if you do something like this, we put a weighting matrix W in the computation. I'm talking here about the fat case. And we get generalized pseudo-inverse. We take weight W, and we can verify that this is a pseudo-inverse. For example, setting this and seeing that is equal to the identity. Then one fact is that as before was minimizing the norm, the pseudo-inverse, the weighted pseudo-inverse minimizes the weighted norm, which is instead of it is just the Euclidean norm with the weighting matrix in the middle with W positive definite. And we can use this, for example, to weight differently the joints, which we have one joint which we want to move more than the other because it's bigger, is smaller than the bigger one. We want to move more the lower inertia joint. We can resort to this solution. Then I talk about the singular value decomposition, but I think since we will use them, it's important also to talk about what singular values are. And singular values are just the extension of the eigenvalue to the rectangular case. So let's think about like a matrix A, m times n. And if we think about the matrix A transpose A, we get what? We get a matrix n times n that has some properties. First is symmetric, and we say that the symmetric matrix has n real eigenvalues that we call lambda I. Second, all these eigenvalues are non-negative, greater than, bigger than, equal than 0. And finally, the singular values of A are linked to the eigenvalues of A transpose A by this relationship. So they are just a square root of the lambda I. They are, of course, n. And in the case, for example, redundant case, then matrix A has at most rank m and at most m non-zero singular values. So the number of non-zero singular values is equal to the rank of the matrix. This means that we can use them, for example, to know the dimension of the range space. And we will know that all the singular values are positive till the rank, the one that is the number where rho is the rank of the matrix, while the number of zero singular values tell us the dimension of the null space of the matrix. And because you remember the null space is n minus rank, and is related, and so they are all zeros for there are a matrix that has a rank rho and a number of column n will have n minus rho zero eigenvalues, zero singular values. Okay. Then, now that we define these quantities, we can start to talk about kinematic singularity. And this time we are talking about singularity at the velocity level. Till now we were defining singularities at the position level, also in the orientation coordinate. But this time we want to compute them and find out what are the singular configuration of a robotic arm. Like, for example, this one is a singular configuration. And in a singular configuration, in general, there is a mobility loss, for example, of the end effector point, depending on the mapping we are using. If J is linking the end effector velocity to the joint velocity, then we consider the end effector analysis. It means that mobility loss means that we cannot move in some Cartesian direction of the task space. And related to that, we see that we have a reduction of the rank of the matrix that is no longer of the size of the task space, but is smaller than that. And if you look at that, you can see that matrix of zeros appears, rows of zero appears in correspondence of the direction, if there is one direction like aligned with the axis, where we lose mobility. So there is no joint motion. The zeros means that there is no joint motion, right, that can achieve movement along the direction. And if you look at this, you will have what? You have 3 degrees of freedom for which you want to move 2 degrees of freedom. So you get redundancy. So the robot becomes redundant in the subspace orthogonal to the singular direction, which is we see is the range space. So the space where we can still move is the robot becomes redundant for this. And we see here, for example, in the case of a 3 degrees of freedom 3R robot, that in this situation, we can no longer move along this direction because the arm is fully stretched. But we have infinite ways to move along this plane, okay? It are the other 2 directions, X and Y. This means that if the Jacobian degenerates at the singularity, the dimension of the range space decreases. We saw that. We lost mobility because the rank decreases, while the dimension of the null space increases accordingly. Why? Because of the rank nullity theorem. You remember that tells you that the rank or row space, dimension of the row space, which is equal to the rank, which is equal to the dimension of the range space, plus the dimension of the null space is equal to n. So if the range space reduces, the row space reduces and the rank as well, and the null space, to keep this sum equal to n, needs to increase of the same amount. Okay? Then another point is that at singularity, we cannot, we said that we cannot change the effect of velocity in some direction, but remember that this is only a local situation. You can escape from singularity and then you recover the ability to change velocity in that direction. Finally, the singularity is not a problem only at the singularity point, a singular configuration, but also close to that, because you can have big joint velocity to achieve small and effector velocity close to singularity. Think about the arm, planar arm. You see that because the cosine has this non-linearity, you have, in essence, that whenever you want to map in this direction, you have the cosine of Q1, for example, Q1 dot, cosine of Q1, is the angle. And for big range of Q1, you have the cosine changes quite small. This means that you have big motion of the joints to achieve to realize small linear motion in this direction of the end effector. And this means, this is due to the fact, for example, that the Jacobian is inverse, is close to get singular. So it's like, it's determinant very close to 0. So if you invert it, you will have 1 over the determinant that you use when you invert the matrix, and you will have a big number. So the Jacobian acts as an amplifier. So you can have, for a small motion, you amplify, you need very big motion of the joints. And this can create problem of saturation of the actuators, which needs to move very fast. You see, these are these velocities, could be seen as, right, as velocities. Or infinitesimal displacement is equivalent. So we want to compute these singularities, but finding the singular configuration of a robot with a big number of joints is not easy, it's computationally complex actually. And to compute them, we can try different ways. In the case of a redundant robot, non-redundant robot, where m is equal to n, we can check, as I said, we have the inverse, so we can check the determinant of the Jacobian matrix and see the configuration where is getting 0. While in the case of a redundant robot, we can check again where the determinant of J transpose, that now is a square matrix, is equal to 0. The problem is that if you do that symbolically for a big number of degrees of freedom, MATLAB, symbolic MATLAB toolbox explodes and is quickly becomes intractable. The other way we could use is to exploit the definition of determinant and find the configuration such that all the square minors of the Jacobian that you can extract from the Jacobian have determinant equal to 0. So you can extract all the square matrix from the Jacobian, check if where they are zeros, the determinant is 0, for which configuration all of them have determinant equal to 0. But think about, for example, a Dexter robot that has 8 degrees of freedom and has this Jacobian matrix sim size 8. How many combinations, how many minors we need to check to check the singularities? Where are the singularities? In your opinion, how many determinants we need to compute? How many combination of 6 columns out of 8 columns exist? You have an idea? You done some statistics. This is tell you something. What does that? What does the exclamation mark? Factorial. Oh my God. Oh. Factorial number, yes. So 6 factorial minus 8 minus 6 factorial. We divide this by this is 8 times 7, and this is 2 factorial, which is 2 times 1. So it's 56 divided by 2. We need to check 28 combination, quite a lot. So in these cases, the trick is to express J in a frame where J becomes simpler, and you can have easy computation of this configuration. Then what are the type of singularities we can encounter in our robot? We can partition them in two big classes. One is the boundary singularity, that are singular configuration that corresponds to points in the Cartesian space that are on the boundary of the reachable workspace. You remember reachable workspace that we found 2 lectures ago? Then there are that configuration where the arm is stretched, completely stretched, or completely retracted, or completely folded. And for example, there are an example are elbow lock in the case of a clear robot. And you see that in this case, doesn't exist a set of Q1 dot, Q2 dot, Q3 dot that is able to move in this direction. The good news is that this kind of singularity can be avoided because they are just at the end of the workspace. So setting some kinematic limits to the joint configuration, setting some joint limits, we can prevent the arm from completely stretching, and so we can avoid to get close to this singularity. Close to this singularity. The other set, instead, the other set that belong the singularity that are internal. They are inside the workspace, and usually they are related to the alignment of 2 or more joint axes, or to the fact when the end effector is on some joint axis. So for example, this is the case of a shoulder lock, where you have the end effector along the axis of the shoulder joint. And you see here that to the same end effector position correspond infinite Q1, sorry, Q1 dot. You, in essence, you cannot exist infinite Q1 dot that Q1 that correspond to that configuration. So yeah, in this case is sorry, it's shoulder lock is singularity at the position level. Yeah. Sorry, I need to check more about these ones because these are singularity at the position level, and maybe I should have explained not in this lecture. So for now, let's keep them with a question mark, and I will check better how to put them. Probably we will move in another lecture. So yeah, in this case, we saw that in the case of Euler angles, when we have 2 axes aligned, it's the same situation. We have infinite Q1 and Q3 positions relative to they correspond to the same end effector position. So we have infinite solutions in inverse kinematics. Then, but let's concentrate on this one. And you see an example here of singularity of a planar robot. And in this case, we have, let's say, we define a task as the only position in the plane of the end effector. We don't care about the orientation. So we have a m times 2 task space, and we have the direct kinematics written like this. We saw that. And to compute the singularities, we want to compute the determinant of the Jacobian. To compute the determinant of the Jacobian, we need the Jacobian. So we do the partial derivative of px with respect to q1, and we get min minus L1 as 1. Then also minus L2 as 1, 2. And we also get the partial derivative of px with respect to q2, and we get minus L2 as 1, 2. Partial derivative of py with respect to q1, L1 cosine of 1 plus L2 cosine of 1, 2. And partial derivative of py with respect to q2, we get L2 cosine of 1. So the Jacobian is 2 times 2 matrix in square. If you compute the determinant, we get what? Minus L1, L2, so we do the cross product here of the elements. S1, and then the second term times this, minus 2, minus 1, 2, cosine of 1, 2, minus this times this, and 1, minus becomes a plus because of a minus here, and 2, S1, 2. Now we have a plus again of this and this, C2, C1, 2, L2, S1, 2. You see this one, oh, sorry, here it is. We're missing. I think I did a mistake. This is L2. So it's L2 squared, C1, 2, S1, 2. This goes away with this one, and we get minus L1, L2, sine of 1, cosine of 1, 2, minus C1, cosine of 1, sine of 1, 2. And this is because of the trigonometric identity is sine of q1 minus q1 plus q2. So is sine of minus q2. But because the sine is an odd function, we know that this is equal to minus sine of q2. Write it explicitly here. And so we can check this in a symbolic way. It's simple, it's a single equation. And the single equation is sine of q2 equal to 0. We see that we don't have any dependency on Q1. And this corresponds, for example, to the two situations where you have the arm stretched or completely folded. Because with Q2 equal to 0, Q2 equal to pi, the sign goes to 0. Then if we look at the singularity that we computed, the boundary singularity usually have the feature to separate the joint space, the configuration space, into two parts where we have the two distinct inverse kinematic solution. Remember the elbow up, elbow down. So a singular configuration is where you pass from the one solution to the other one. This is another note, final note that can be done. Okay. Then we can do another exercise with the RRP robot. Then I think we can do the break, or we can do the break now. We'll continue in 10 minutes. Okay. At 52, start again. In the meanwhile, I understood what was the issue with the with internal singularities, the shoulder one, for example, and we will see an example here. Actually, the fact that we have the end effector on the shoulder axis, it means that we are in a singular configuration because the Jacobian, the rank of the Jacobian reduces. And for example, if you want to move this and effector velocity, we have infinite Q1 dot motion that can achieve this. So you remember, we lose mobility in one direction, or we become redundant with respect to the task. Now, if we write the direct kinematics of this robot, which is a RRP robot, so rotational prismatic joint robot, we have this expression for the end effector coordinates. And again, we want to compute the analytic Jacobian with partial derivatives. And we do the partial derivative of the px with respect to q1, and we get q3 minus sine of 1 c2. Then px with respect to q2, we get minus q3 c1 s2. With respect to q3, we get c1 c2. Then py with respect to q1, we get q3 c1 c2. py with respect to q2, we get q3 s1 s2. And q1 py with respect to q3, we get c2 s1. pz with respect to q1 is not there, q1, so it's 0. pz with respect to q2, we have q3 cosine of 2. And pz with respect to q3, we have s2. And this is the Jacobian. Now, if we compute the determinant of this, we will see that in MATLAB, we get this expression q3 squared c2, cosine of q2. We have that this becomes 0 when so where q or so cosine is 0 at 0.
No, or
Plus or minus? Okay, good. Okay, so let's analyze the kind of singularity. Case 1 is wherever we have q3 whatever and q2 equal to plus minus pi half. And we see that in this case, we have a simple singularity. Why simple? Because the loss of rank is only one. So we go from rank 3, maximum rank, to rank 2. So we lose mobility on one direction. While in the case of free, we have the third joint, this one, fully retract. So you think that collapses on the shoulder axis. And in this situation, we have a double singularity. Because the rank drops to 1. So we lose 2 mobility in 2 directions. And these are the internal singularity we were talking about. Now we can draw them. How do they look like? We see that in this case, for example, these are, we can relate the singularity again to the inverse kinematic solutions. We see that we have the 2 regular solution in case we are out of the singularity, whereas we are at the singularity, we have infinite solution for Q1 joint related to this indefective position. And the joint is vertical or completely folded here. This is the Q2 joint. And in the case the Q3 is folded, we have in essence that this point goes to here. So we have the end effector at the origin of the second joint. So it means that to achieve this end effector position, we can set any Q1 or Q2 value of the joints. So any Q1 or Q2 position we bring to this point. That's why we have double singularity here. And these are on the shoulder axis. While in here we are we have infinite solution for Q1. But we can move Q2. And Q2 has some values. Okay. So in essence, here, for example, we lose mobility where we can move, let's say this is the Z axis. We can move along the Z axis. We can move along the X axis. Yeah, forget. I need to work this out better. This was not clear. Another exercise is the one of the subspaces. So in this case, we have the planar 3R robot. So it is lying on a plane. In this case, we have the task space that is dimensional, and the effective position is in the XY plane, and the joint space is three-dimensional. If we want to analyze the range space and the null space in this for this robot at some specific configuration, one is a singular configuration, one is the non-singular one. Let's start with the non-singular one. So we know that the singular is whenever, for example, a singular one is whenever the arm is completely extended or is folded, and this is a generic one. And the range space tells me, replies to the question, can I go everywhere or not? Can I move everywhere? And to know if this is possible or not, we need to check the rank of J and see if it's true. The other question to answer is, can I move the joint such that the end effector doesn't move? And to reply to this one, instead, we need to check if the exists a null space. In MATLAB, we compute a null space basis and check its dimension if it is bigger than 0. And a null space basis, remember that it is a minimum number of linear independent element of a vector space that can generate all the other vectors of the vector space. So having a basis, we in essence be able to represent all the vector space. Then the second exercise, what is the dimension of the range space? We check again the null space basis we compute with the function null of J, and the range space basis we compute with the orth J. So we check the dimension of that. And we repeat this experiment for a singular configuration. Let me say, for example, is the situation where you have the arm completely extended. And in this case, MATLAB tells us that the Jacobian drops rank and becomes this one, where we have rows of zeros. And we see that in this case, the rank is no longer 2, but it becomes 1. So it means I cannot move, for example, in the y direction, while I can move in the x direction. And the null space is 3 minus the rank of J, so it's 2-dimensional, and this is a null space basis of dimension 2. While the range space is the green one, is monodimensional because it's rank of dimensional task space 2 minus the rank. Remember m minus rank, and is it's just 1 because it's equal to the rank of the matrix, and this is one base of the range space. And as you see, this is exactly this direction. So if we put a minus alpha here, I can get vectors in this direction, and otherwise, if I put plus alpha, I get vectors in the other. So this represents a direction on the along the parallel to the x-axis, and it's the only direction where the effector can move. Okay. Now let's see what are the issues at singularities. So in the case we said we cover the inverse kinematics at the position level, but to cover it also at the velocity level, we use the formula, the inversion of the Jacobian that maps and the factor velocity into joint velocity, and this Jacobian needs to be inverted, needs to be squared and non-singular, square and non-singular. And if there's a singularity, is no longer J is no longer invertible, and we saw a trick to make it invertible for redundant robots where J is rectangular, where the inverse is not defined, but we can use the pseudo inverse that is defined, is always defined. But what happens whenever we have there is a loss of rank in J? So you remember we go back to the case wherever we the pseudo inverse finds a solution, not exact, but it is as closest as possible to the desired the factor velocity. So in this case, we can see that we have the range space that present a feasible velocity direction and the null space of J pseudo inverse that represent the non-feasible direction. So actually, whenever we do the pseudo inversion, we get the Q that realizes the range space component, okay, of the velocity. So in essence, if you have our velocity here that has a non-feasible part and a feasible part, you remember the feasible part stay in the range space, we end up in essence inside here. So we will filter out the null space component of J transpose J pseudo inverse, and we'll get the range space one. Now, what are the problems of singularity? As we said that there are big joint velocities close to the singularity, even though we are not at the singularity. And so at the singularity, we said that even in the case where the J matrix is not full rank, we can invert it with the singular value decomposition. We cannot use the other formula that we saw, but we can use the singular value decomposition. But when we are close, we can always compute the inversion, but we have very big joint velocity. Think about a planar robot that goes from this point, and where is getting close to the singularity. You see here a stroboscopic view of the motion, and you see that the planar robot will always have a elbow down configuration. It will not change the inverse kinematic solution, but will have a very, very fast motion in this moment. And this is because joint velocities can be very high, very close to the singularity. We see that at that point, one of the joints spiked up to 600 degrees per second speed. Even though the Cartesian error, the position error is quite small. So let's say we are using this inverse kinematics to implement we check the error of minus v. And we see that is achieved because we are not at the singularity, but the velocity are very big. And this could not be feasible if I saturated the joints, for example, that cannot achieve such a speed, and then I not able to realize the effector velocity, and I have I will accumulate if I'm doing a controller that tries to control position with using this approach of inverse kinematics, I will accumulate errors. So we need a possible way to check how close the robustity is to the singularity, and to do so, we can check the value of the smallest singular value of the J matrix. We define the singular values before as the eigenvalues of the J. Sorry, this is impulse J transpose. Yeah, J transpose J. Square root of the singular values of the eigenvalues of the J transpose J matrix, that is squared. And if we plot that along the motion, we see that this smaller singular value gets very small, very close to zero. So whenever it's zero, you are at singularity. And we want, therefore, a more robust inversion method than the one we use now with a pseudo inverse. So a way to achieve this is to use the so-called damped least square method that finds a trade-off between realizing the velocity task at the Cartesian level and have at the same time small joint velocity. Again, we can cast this as an optimization problem where we try to minimize, let's say, the error at the Cartesian velocity plus some another cost that tries to minimize the joint velocity. And of course, this other cost term should be smaller, and we have the square cost here and the damped velocity here. And the solution can be obtained in closed form if you set the gradient of this problem to zero, as follows. Sorry. This star means optimal. Or in case of redundant robot, this is equivalent. It's exactly spitting out the same values. You can verify with MATLAB. And you use this expression for redundant robot. So you see that with respect to the pseudo-inverse solution, we added this term, and this is a term that is called regularization, and as the effect of solving a optimization problem where it tries to achieve a trade-off between realizing the desired end effector velocity and while keeping the velocity small. And if we look, so this method can be used both to recover from singularity from a square in case of square Jacobian, or if you have a rectangular matrix Jacobian to invert, also even if it's singular. And the price to pay of this is that if you increase lambda, you penalize velocity, but you get bigger tracking error. So you want to achieve the desired tracking, the desired velocity that you want. But you see that again, in the non-damped case, you have the Cartesian error is very small, while in the damped case it goes a little bit bigger. So it's going to 2.5 centimeter. While in a non-damped case, we have a very fast reconfiguration of the first joint, while in the damped case, we have a completely different solution close to the singularity. That is better behaved, because in one case, in this case, we have a very high peak velocity at the first joint, while here with the velocity peak is reduced to only 80 degrees per second. So use the damping square in case you're sure you're gonna hit some singularity in your workspace when you're, or you can, for example, decide to tune lambda, if you know where the singularity is, to be very small when you're far from the singularity, and then increase it as long as you get close to that. I would like to show you some exercise in MATLAB. Finally, sorry, before the exercise. Whatever is missing is that how do we do whenever we want to map higher order derivatives of the end effector into joints? So let's think we are defining the generic tax function that also include orientation, doesn't matter. And if we want to extend to the acceleration level, we just do the derivative of this function. So because the Jacobian depends on joint configuration Q, we do the derivative of a product rule, and we get J of Q. So the derivative of the acceleration of the end effector, for example, or the task variable is the Jacobian times Q dot dot plus the derivative of the Jacobian with respect to time times Q dot. So this is the way. So if you want to retrieve the joint acceleration from the Cartesian acceleration, we need to do this computation. We will see this probably in one of the labs. Whenever we want to do inverse kinematics, we want to define a trajectory also for the acceleration from the end effector acceleration. And so we need to use this expression. And we can, in essence, summarize the three inverse kinematics at the position of the velocity and at the acceleration level in this square bracket. Now let me turn on MATLAB. taking ages. My God. I have no idea. Well, let's continue with the next slide, otherwise we waste time. Okay. Okay. So yeah, I would like to show you in the singularities. You can just double check the exercise we did for the 2R and the RRP robot. So in the RR case, you get you have the Jacobian, and you evaluate the Jacobian. VPI is just to have a symbolic expression with a certain number of digits, and you replace, in essence, Q2 equal to 0, which is one of the singularity, and you can check if the Jacobian is 0. Actually, yeah, it's barely 0. I mean, we ask for a certain precision, so we approximate it. So is if we remove this, I'm sure that will be 0. Yeah. And the other singularity, for example, could be, again, whatever value of Q1. So we can set 0, 0, and again, we get 0. Instead, for the exercise RRP, this time we define the 4 kinematics. We define the task variable as a vector of px, py, pz. And we can use instead of doing by hand, as we did here, we can employ the Jacobian function of MATLAB that does the partial derivative, computes the Jacobian matrix from vector R with respect to the vector Q, and just spits out the Jacobian in a symbolic way. So this is just to check if you want to check your computation. Then you can compute the determinant. Of course, you want to apply the trigonometric identities, formulas to simplify, and get out the values we were analyzing. And again, you can check the 2 exercises configuration. The first one with the single singularity, where we have a generic Q1 different 0.5, Q2 pi half, and Q3 0.5. And we see that a single singularity, if we compute the determinant drops only of 1, so it becomes 2. Then in the case of a double singularity, that was the case wherever Q3 was 0, we get a drop around, you see 2 columns of the Jacobian becomes 0, so the rank we expect to be 1. While in the exercise of the to show the spaces analysis. Again, we put inside the direct kinematics. This time we are talking about a 3R planar robot, free rotational joint planar robot. We computed Jacobian in the same way. Again, define P and Q. This time in a slightly different way. And we replace the configuration that is generic, you remember, was in the middle of the workspace. And we see that the rank is 2, so it's full rank, there is no singularity. While we were asking if there was a null space in this configuration. So we compute the null, use the null function of MATLAB to compute a null space basis of J, and we find out this column vector. So the null space exists. Its dimension, which is the size of this, is 1, of course, and we can verify that is a null space by pre-multiplying J times this null space base, and we get 0, 0. This is just e to the minus 41, so very small number. It's almost 0. The exercise 2.2, it was to compute use the orth function of MATLAB to compute the range space basis. And in this case, we get what? We have rank of 2, so we get a two-dimensional range space, and which bases are these 2 columns. And the dimension, as I said, is 2. And while the null space of so the dual of the range space of J is the null space of J pseudo inverse. So we compute the pseudo inverse with PIMV, we compute the null space basis, and we expect to be what? 0, because M is 2, range space dimension is 2, so M minus 2 is 0. Then the total dimension is 2. In the circular case, instead we have the range space of the pseudo inverse of J, which is 2-dimensional. And see, this means that if we sum up the range space of J pseudo inverse with the null space of J, which was 1-dimensional, we get the domain that is 3-dimensional. So the theorem is verified, and now we want to evaluate the Jacobian in a singular configuration. It is pi half, you remember, 0 and pi, or 0 in this case, sorry. And we get that a Jacobian that has a rows of zeros, so the rank now is reduced, it's only 1, and the null space become 2, because we have 3 minus 1, 2, size is 2, this is a null space base, and then we can verify, for example, that this is a null space by pre-multiplied by J. We can understand, for example, that any combination of a column of the null space base can be combined and is still a vector that belongs to the null space. So, for example, in this case, we combine with different scalars the 2 columns, and still we get that if you multiply by J, we get 0. Then, in this case, the range space size is 1, because we have rank 1 and M is 2. So, sorry, because we have rank 1 and the size of the null space of J is 2. Because it's 3 minus 1 rank is null space size 2. So we covered the exercise. Now we can continue with the next set of lectures that you have any question about this? Everything was clear? Okay. Online as well as everything is okay. So let's introduce the new chapter, the course, which is dynamics. And before talking about motion, we want to start talking about, so till now we describe only the motion with kinematics, and we didn't think about the causes of the motion that are the forces that generate the motion, for example. But before talking about motion, we want to introduce the chapter about statics. And we will see that as exists a mapping for velocities, the Jacobian that maps joint velocity to end effector velocity, if we transpose the Jacobian, this becomes a mapping that maps forces, Cartesian forces, into joint torques or generalized torques, generalized forces. And this is exactly entering in the problem, in a specific problem, statics, where the robot doesn't move, but is in balance under the action of several forces. Okay. We see here a sketch of a robot with a different set of joints, prismatic and rotational. And the robot might enter in contact with the end effector, with the environment. And for example, if you have a tool, you want to do some operation, and the fact that you are in contact with the environment doesn't mean that there is a force. You could be in contact without applying any force. So you cannot recognize that you are pushing from geometric consideration. Okay? You need to check if you're pushing, you need to check at the values of the torque of the robot. And to check that, you need to define the relationship between the joint torques. This, of course, is tau free, but it's a force because it's a prismatic joint, so a linear force, not a torque. And between the joint torques and the effector force. Okay. So at the end effector, there is no actuator, but the effect of the whole set of joint torques will create a force at the end effector. And let's define also Fx as the force that the environment applies on the robot at the end effector. And because of the third principle of dynamics, of action and reaction, we know that this force is not independent from this one. If a body applies a force on onto another body, and this other body will apply another force, that will be in equilibrium or not, dependent if the body moves. So if there is an acceleration, part of the force will be creating some acceleration. Otherwise, there is a perfect balance. Okay. So tau are force and torques exerted by the motors at the joint, and F is the equivalent force that results from this joint effort at the end effector, and Fx is the forces that the environment applies at the end effector, that in case of statics is opposite to F. Okay. If there is motion, this is no longer true. Okay. Now, we want to put in the same side of our dynamic equation all the generalized forces that are performing work on the robot. So the positive work is when the work is done on the robot. And among the forces that can do work on the robot, we have both the motors, the joint torques due to the motors, or also the environmental forces. So, yeah. So what are the joint torques that will balance an external force exerted by the environment? To find this relation, we think that, let's try to think that the robot is not moving, but we want to define some infinitesimal motions to understand how the force is exchanged. And this infinitesimal motion will be consistent with the constraint, with the joint constraint. So we will have, cannot be any motion. So there will be the same motion that a joint allows. And that's why we introduced the concept of infinitesimal displacement. That is the motion allowed by the joint. But this has also virtual displacement. So they don't happen in fact. So they're just infinitesimal. And the fact that this motion are almost barely zero means that there is no kinetic energy variation and the velocity is zero. So there is no dissipation in statics. So the infinitesimal displacement, as we defined for the joints, can be also defined for the end effector, like infinitesimal displacement at the position or even at the orientation. And this will be related to the infinitesimal displacement at the joint by the Jacobian. So the same as velocities we can do for infinitesimal displacement. Now let's define the principle of virtual work, that is the head, the main ingredient in statics. And the principle of virtual work claims that the sum of the virtual work done by all the torques or forces acting on the system is zero at the static equilibrium. So think about, there are torques at these joints, and each torque is doing a infinitesimal work. For example, tau 1 does a virtual work on a displacement with the displacement dq1, tau2 does a virtual work whenever there is a displacement dq2. And we can compute the total work of all the joints doing this scalar product of the torque vector times the vector of infinitesimal displacement of all the joints, minus, you remember, the external and the factor, the external forces at the end effector that are minus fx. Sorry, that are minus f. So this is the work that is done by the external forces on the end effector infinitesimal displacement. And we said that this is J dq. And the principal virtual work says that all these things that make work on the robot, they are, the sum of their work is 0. So if we collect the Q from this, we get tau transpose minus F transpose J. And for every Q, we can, if we want, because we want this happening for every Q, delta Q, sorry, we want that this is true. And from this, we get, in essence, the principle of virtual work consequence, that is the torques that compensate D and the factor forces are minus J transpose Fx. That the robot, the environment applies on the robot. Otherwise, if you want to compute the equivalent and the factor force due to the set of joint torques we apply at the joint, then we use this other expression. So I just noticed that I'm opening the wrong file. I want to open okay. 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 Everything is clear till now? Oh, I forgot to share the screen. Oh, I need to share the screen now. Share the screen. Okay, so we want to define now some duality between velocities and forces. We saw that the Jacobian maps velocity into Cartesian velocities, joint velocity to Cartesian velocities, or virtual displacement. But we also saw that the J Jacobian transpose does the opposite. So we have an inverse path, but on dual quantities. And thus, the Jacobian transpose maps force and moments at the vector into force and torques at the joints. And we see that the size of these spaces are the same, even though they contain different vector types. If the rank of J, since the rank of J is equal to the rank of J transpose, it means that if they lose rank, they will do at the same way. And this means that the analysis of singular configuration that we did for the at the velocity level, it will be present. It will be the same, and also at the force level for the force mapping. So similarly to what we did for velocities, we can do the same analysis of range space and null space, but this time we consider as mapping not the Jacobian, but the Jacobian transpose. So here we pass from end effector velocities that lives in Rm, and through the Jacobian transpose, we map into the range space of J transpose, where live torques that usually are vector that are in Rn. So if for velocities, the range space of J was describing the Cartesian velocity that could be generated with some joint velocity, in the case of range of J transpose, we have torques that can generate some Cartesian force. Okay? While in the null space of J transpose, so let's write this before. So these are the joint torques that can generate or balance in the vector forces. And this is a set represented by the vector tau belonging to Rn, such that it exists a force in Rm where J transpose F is equal to tau. While in the null space of J transpose, instead, what we have, in your opinion? Yeah, but what are they? Give an intuition of this. An intuition of what represent these forces. What are these forces? Because you need it's good to give a definition, a mathematical definition, but you always need to have an image of the concept in your head. Otherwise you forget. Balance each other. Look at what they do whenever they go to the joint. They don't need any torque. So there are forces that are balanced by the structure itself. Don't need any torque for balancing. The torque in null space J transpose are these ones. I extend my hand, I push against the wall, and I don't do any effort with my muscle because all the force that I generate is generated by my bones. My bones generate the force against the wall. I don't use the joint. If I go in this configuration, I need to generate this force, I need to push with my joints a bit. And if I go in this configuration, I need to push a lot. Okay. So these are the forces that are balanced by the structure. And correspond to zero torque. Okay. So to define the non-space of J transpose in a mathematical way are the Cartesian forces such that J transpose are equal to zero. Okay. Very good. So now let's do some analysis on this. We have two cases that we are interested to, right? Apart from the SCARA robot, but we can, so in the for a non-redundant manipulator, we have two cases according to the fact that the Jacobian matrix is as full rank or not. So let's see at first the case of full rank. And we see that we move in case of full rank from a space of, sorry, this is the case of m equal to n. So we move from a set the same dimension for the domain and the codomain. And in these cases, there is no null space for J and no null space for J transpose, because the rank is equal to both the column and the rows. While if the rank is of J in J transpose, this is J in J transpose. If the rank is smaller than the size of the matrix, then we do have a null space for J and also a null space for J transpose. So we have some velocities that doesn't produce any end-effector velocity, and we have some Cartesian forces that don't need any torque. They are all on the structure. And we see that of the two sets, we have the same size of null space, both for J and J transpose. While for redundant manipulators, it is a second case we are interested to. J transpose is rectangular, and this time is skinny. We have more rows than columns. Okay, it's because well, we have torques here. Sorry, torques, and on the here we have forces. Now, if the Jacobian is full rank, well, in this case, rank is equal to m. Okay, then do we have a null space for J in a redundant manipulator? redundant manipulator J as null space. So when I talk about J, we are talking about velocity. So all the discussion, previous discussion, this is a tricky question. Huh? So we have a null space because we are talking about a redundant manipulator, but for J transpose, that is the one that is drawn here, we don't have it because the rank is equal to n. Okay. So in the case of a full rank, and again here the null space could happen only in this set, not in this set. So if we have, since J transpose is mapping from Rm to a bigger set, then the null space could be only here. And in fact, this is the situation. We have a null space for J here in the codomain, in the domain, sorry, and we don't have it for J transpose. While if rank is J transpose is lower than M, then we do have both a null space for J because we have a redundancy as before, and also we have a null space for J transpose because we have a polynomial 0 here, so we have M minus rank, the dimension of the null space of J transpose, and we end up in this situation. So again, we have a bigger set here, then a smaller one here. We have a null space in both. Okay. Let's do some an example. We try to compute these spaces, and again we take our old friend, the case of a planar QR robot, and in terms of velocities, let's consider. What are our data? So it was given by the wrong thing. We have a planar robot. We have M equal to N, 2 degrees of freedom, and the task is two-dimensional, X and Y. And the rank is equal to M. So we have full rank case, and in the full rank case, we saw that the range space dimension is 2, so it's the whole R squared, and you can move everywhere here, while the null space of J transpose doesn't exist. While for forces, this is for velocity, so we want to analyze the null space of J, and the null space of J doesn't exist because we don't have any redundancy. While for forces, the range space of J transpose is R squared because the rank is 2, and the null space of J transpose is 2 minus rank of 2, so it's 0, the dimension. So again, doesn't exist. When I say doesn't exist, I mean it exists in sense that it contains only the 0 vector, because the 0 vector you can always multiply for J and you get 0. That is a trivial case. Then let's compute this in the case of a singularity, wherever we have m equal to n, again, the square case, but this time we have a rank lower than the m or n, the size of the matrix. And in this case, we know that for a planar robot, we have singularity at Q2 equal to 0, and the Jacobian we evaluate at that. If you evaluate at that configuration, we get this matrix where we see that the second column is L2 divided by L1 plus L2 times the first column. So these two columns are not linearly independent. This means that we have rank deficiency in the matrix, and we have rank 1 instead, because the only linear independent vector is one of the two. So if we want to compute the range space, how does the range space looks like in this case? So we want to represent all the columns with one vector. What is the vector that you can represent? You can represent all the columns. Sine Q1, cosine Q1. There's something missing. Represent this column. Minus sine 1, okay. So multiply by scalar alpha, we can have this, and let's draw it. So you see, take any vector that has this component, and you see, you find the direction of the range space, because sine Q1 is this, minus sine Q1 is this vector, and cosine Q1, this is Q1, and cosine Q1 is this vector. Sorry. Well, you can verify that this vector is represented by this direction, and if you multiply by alpha, you can get all the vectors in this direction. So you represent the mobility at this configuration that is singular. And in the case of the Jacobian transpose, let's find the, so sorry, I didn't do the analysis here, but so the range space is one dimensional, the new space of J transpose, new space of J, it's 1 minus 2 is monodimensional again. Range space of J transpose is one dimensional because of the rank, and null space of J transpose is two minus 1 equal to 1. So if we want to compute the null space of J transpose, we can find a vector V sorry, not V, F, so don't confuse, such that J transpose F is equal to 0. And if you have this J transpose, we will see that if you choose this vector to be cosine of 1 and sine of 1, you will have that if you multiply by J transpose, you get zeros. And if you look at that, where is this direction? It is a new space of J transpose is exactly along the kinematic axis. And these are the forces that are absorbed by the structure. I did the example before. Okay. While what remains are the range space of J transpose. And in this case, what is the column that represents, this is one dimensional, represent both of the two columns here.
And one plus L2.
Okay. Yes, because you need to think about S1 and S1 as a number. So you're just, this is a number and this is another number. So what you do is you multiply L1 plus L2 and L2, these are the scaling factor, then you multiply for a number that you can put it here, you can represent all the two columns with giving different values. So with the same, the two columns are linearly dependent and they are related to each other with the scalings. Then for the new space of J, again, we want to find a vector that nullifies these two columns. And if we choose, for example, L2 and minus L1 plus L2, we can see that these two terms will be zeroing, and if we multiply for the second row, also these two terms are going to zero. So, and this is an interesting situation because you can think about you're using L1 equal to L2 equal to 1. If you can think that whatever motion you are giving to this joint in this direction, the other one should be minus that showing motion that you did for that joint, minus 2, the double of this motion in the opposite direction, and this will make such that this point doesn't move, which is exactly what we want to represent with the new space, that we move the joint, but the end effector doesn't move. It's just comes out from the expression of the new space. Then to finalize the lecture on statics, an important application of a principle of virtual works is when we want to, for example, map force and moments at different places of a rigid body. And this is the case, for example, when you want to compute forces at the end effector or the tool. and you have your readings that are coming from a force sensor that is located along, for example, the last link at, I don't know, 20 centimeter distance. So it's not exactly the point where you compute the force. So you measure the forces here, but you are interested into get an estimate of the forces in this point or in this point, where the end effector is applying. And this, think about, you have a 6-axis force sensor that measure the forces. So we want to find this mapping that maps the moment and force, because they are 6-axis force sensor, read at the force sensor frame into moment and force at the end effector frame FB. And to do so, we start from velocity transformations. And then, as we did for the Jacobian, after we found this relationship at the velocity level of angular and linear velocity, we want to map from one frame to the other, we can do the same using the duality concept, taking the transpose of this mapping and get the expression for forces and moments for free. So recall the slide on differential direct kinematics that Octavio did. And first, we consider a mapping between linear and angular velocity defined in different frames, FA, FB of a rigid body. We know that while the linear velocity changes from a point to another point, the angular velocity is the same on all the points of the rigid body. And so the force velocity of a point A in frame A can be expressed as the velocity of a point B, frame A, plus the angular velocity of frame B, again expressed in frame A, vector product, the vector that is going from the origin of frame B to the origin of frame A, or frame A, in frame A, expressed in frame A. And then we rewrite this, we revert the cross product, putting a minus. We want to express the velocity of B, point B in frame B. And with the rotation matrix, so first let's use the skew symmetric matrix to represent the cross product in a linear way. And then we want to do everything in terms of frame B here. So we rotate. You remember the rotation. If you rotate a vector inside the skew symmetric, you can put it out with the rotation matrix and its transpose. So we do this from B to A, and this is goes from A to B. Yeah, so let's do that explicitly. Can you remember this property? So it's R something like that, right? By the way, if you, the final result, if you apply this property, is get B way omega B in frame B. So this is, if you apply that, you will get to here. And you can collect everything in a matrix that is like this. And you collect the VB. While for the, this is for the linear velocity, but for the angular velocity, we say that the omega is the same, omega, and is related to the omega in B, expressed in B frame is just related to the omega expressed in A frame by the rotation matrix RB. Yeah, this is a rigid problem. Okay, this holds only for E. Otherwise, we would have a joint in the middle, like we did for the Jacobian computation. So if you put everything together, we get both omega A and BA equal to RBA times RBA BA. We have VB in B, and as omega we said it is the same. And here we have just the rotation matrix for omega. And we call this transformation H. So we said that we want to employ the dual, the computed dual for forces and moments. So we just take the transpose of this this mapping. We get the forces. So you remember this mapping is from frame A to frame B, and the transpose one will be from frame B to frame A, because as we did for Cartesian forces, so Jacobian maps joints into Cartesian quantity, Jacobian transpose Cartesian quantity into joint, and here it's the same. We flip the frames, and this is the moment in B frame. And we have A, B that we computed before, transpose times the force in frame A and the moment in frame A. And this, how does it look like? We do the transpose of the previous expression, we get RBA transpose. We flip the 0 that was on the lower left, we get on the upper right. Then we do a transpose of this term that is this way, and RBA transpose. And this will be, we flip the frames, so we get RBA here, get a 0 here, we get RBA here, and we do the transpose of the first one, sorry, the second one times the transpose of the first one. And sorry, we have the function, yeah. So we get, and because the transpose of a skew-symmetric matrix is minus the skew-symmetric matrix, we get that this minus goes away, and we get this times RAB transpose, that is RBA. Okay, and this is the expression for a B transpose. Okay. Okay. Yeah, if you have questions, otherwise I will close here, because then tomorrow we can continue with the dynamics, with definition of a Euler-Lagrange method, and also I think the Newton-Euler one. I think Octavio will prepare, will put some exercise on this in this mapping, because it's quite useful whenever you need to read a sensor, and so you will have some exercise on that as well.
Yeah, for the lab session, I will add some exercises on this.
Okay. So see you tomorrow. Have a good evening for everybody.